Hey everyone, today, very interesting discussion. We're going to talk about the dorsolateral prefrontal cortex. This is a very important part of the brain to understand. They believe that the dorsolateral prefrontal cortex is the seat of the ego. Remember the ego? Look at my series on the ego. I go in depth about how if you understand the ego, you understand your suffering. You escape the ego, you escape your suffering. Simply put, how do you end your suffering? Escape the ego. Even more simply put, how do you escape your ego? End your ignorance. That's it. Your suffering comes because of your ignorance, right? And once you understand the ego, you can finally separate from it and live a life independent of it. You don't have to be a slave to it anymore. These are very interesting concepts that I teach on this channel, the Reed's Matrix. So take a look at this channel. It's very interesting. And so we're going to go ahead and look at GGP, and I'll show you about the prefrontal cortex and actually the circuits. And we want to understand the function of the prefrontal cortex, of the dorsolateral prefrontal cortex. We want to know the circuitry and things like that. We want to know the receptor profiles. When patients present with symptoms, what do they present with when damage to the prefrontal cortex, dorsolateral prefrontal cortex? It'll be very interesting here to know, right? Sounds good. So let me take a look here. Okay. Okay, so let me go ahead and do I need to clear this? Okay, new chat. Explain the dorsolateral prefrontal cortex with emphasis on network okay, explain the morals lateral dorsal. Okay, dorsolateral prefrontal cortex with emphasis on network responsibilities and symptoms and focus on receptor profiles. Okay, let me see what's happening here. Okay, what's happening here? Okay, it's pulsating, so I think it's thinking. You know what? I didn't explain this correctly. Let me stop this. I spell things incorrectly here. Okay. DORS. Okay. Explain the dorsolateral prefrontal cortex. Okay. Emphasize the network, let's say architecture, network layout, symptoms, and focus on receptors, receptor profiles in the network. And this network. Okay, great. Okay, I think we have it here. Okay, excellent. Let's take a deep look at the dorsolateral prefrontal cortex, that DLPFC, dorsolateral prefrontal cortex, focusing on its neuroanatomical layout, right? Symptomatology of this function and neurochemical receptor profiles. Great. The dorsolateral prefrontal cortex is one of the most critical regions for executive control, working memory, goal-directed behavior, and cognitive flexibility. You see this executive control, executive reasoning, like working memory, the number of items you can remember at one time in your memory to sort of manipulate things. Goal-directed behavior, multitasking, coordinating time, sequencing tasks, cognitive flexibility, the inability to switch perspective and change perspective or update your theory with new information. Anatomically, it corresponds roughly to Brodmann's area 9 and 46, located on the middle frontal gyrus of the prefrontal cortex. Let me show you what that looks like. So images, okay. So Brodmann areas over here. Okay, dorsolateral prefrontal cortex. Dorsolateral prefrontal cortex, area 9 and 46. Okay, area 9. So these are coronal section, area 9. Okay. Then area 46. So the dorsolateral frontal cortex is the seat of the ego. And so, wow. And so when we talk about the ego, this mapping out is probably the best example that we have of the ego. It's amazing to see it. Okay, look, dorsolateral prefrontal cortex here. Yeah, dorsolateral prefrontal cortex here. Look, yeah, I see it on each side now. I see it. I see what. So this is the anterior. This is the person looking at you, and I can see on each lobe there. Here's a side view on each lobe there. Here's the anterior view. You don't have much on anterior view. Here's the coronal section here, and then here's the underside of the brain. Yeah, I can see how that dorsolateral prefrontal cortex. Yeah, so look, dorsolateral prefrontal cortex here, dorsolateral prefrontal cortex. Yeah, here's dorsolateral prefrontal cortex. I can see that. Yeah, this is when you think about how the ego functions. Look, Brodmann areas. Yeah, both Brodmann areas 9, Brodmann areas 46, area 9, area 46. I wonder the significance of area 9 and area 46. Area 9 and area 46. How did they come up with that matching? I got to look up that Brodmann's area. Areas 9 and 46. Why do they call it area 9? Okay. Okay, the dorsolateral prefrontal cortex is one of the most critical regions for executive control, right? This executive functioning skills, working memory, that's the number of items you can have in your memory all the time, goal-directed behavior, and cognitive flexibility. Okay, it's part of the frontal striatal circuit, loop forming between the dorsolateral prefrontal cortex, the dorsal caudate nucleus, the dorsal globus pallidus, the mid-dorsal thalamus, and back to the dorsolateral prefrontal cortex. There's that loop again. This loop underpins executive function, integrating sensory input, motivation, and motor planning into coherent goal-oriented behavior. This makes sense. It makes sense. Network layout and connectivity. The dorsolateral prefrontal cortex, all this time I didn't have this up there. All the time I was good. All this time. Okay. Great. Network layout and connectivity. The dorsolateral prefrontal cortex is highly interconnected with large-scale and subcortical networks. So the dorsolateral prefrontal cortex is highly interconnected within large-scale cortical and subcortical networks. That makes sense. Remember those large striatal fibers that come from the frontal lobe, frontal cortex down? Yeah, cortical connections, like I said. The posterior parietal cortex, superior temporal gyrus, anterior cingulate gyrus, orbital frontal cortex, premotor cortex, and suprarenal motor areas. So these are corticals. The posterior parietal cortex is the integration of spatial and attentional information for working memory. The superior is the auditory and language-related processing. The anterior cingulate, performance monitoring, error detection, and conflict resolution. Orbital frontal, emotional, reward-related input fluctuating, influencing decision-making. And premotor cortex, planning and initiation motor counteractions. You can see how these different centers have different responsibilities, right? Subcortical connection, the dorsal striatum, that's the caudate nucleus for critical for cognitive aspects of movement and habit learning. And the thalamus relays, processes information back to the cortex, and the cerebellum involved in fine-tuning cognitive sequences and timing. Look, functional networks, the frontal parietal control networks. This is a flexible top-down control of attention and working memory. The central executive network maintains and manipulates goal-related information. And here, antagonistic relationship with the default mode network. This suppresses deep dorsolateral prefrontal cortex, suppress internally focused DMA activity during task engagement, whatever it is. So here, let me go ahead and look at the receptors on this dorsolateral prefrontal cortex. The dorsolateral prefrontal cortex has a rich, and then let me show you here what I was looking at before. Here is the some imaging studies here, okay, and this is like a top-down version of it. And as you can see, when you go deeper into the brain structure, you can see here Brodmann area 46, Brodmann area is 49. And then as you go higher in the brain structure, you get more Brodmann area 9. And then blue is Brodmann area 9. So look, on each side of the frontal lobe, it'll be located like on each side. Here's another example of a brain. Here's the okay, yeah, this is the what? Okay, so this is the frontal lobe and this is the rear. Okay, so this is the dorsolateral prefrontal cortex here on the left side, here's on the right side. This is like the insular surface of the brain, so there's no much activity there. This is a coronal section here, and it shows the activities of the dorsolateral prefrontal cortex bilaterally. Here's another example of the dorsolateral prefrontal cortex here on the left-hand side, here on the right-hand side. Here is the insular surface. Okay, here's the anterior surface underneath. So it shows you the regions which will form. Look, the dorsolateral prefrontal cortex in this region here, it will be in that region, also in this region. Here's a coronal section, the dorsolateral prefrontal cortex here, as you can see here. Yep. Okay, here. Okay. Next, let's look at the neurochemical and receptor profiles of the dorsolateral prefrontal cortex. The dorsolateral prefrontal cortex has a rich and complex receptor landscape reflecting its integrative cognitive role. The key neurotransmitters are, look, the dopaminergic system. There we are again. Look, here we are at the glutaminergic system. But there we are again. Guess what? GABA. If you got a glutamate to turn things on, of course you have GABA to turn things off, right? And then we have norepinephrine to stir things up. excite everything. And then we have serotonin to make everybody fall in love and cheer and sleep really well and feel and bind and connect. So the same neurotransmitters, the same family here, and the same receptor profiles. So let's go through them real quick, right? So the dopaminergic system, the primary receptors are D1 and D2 receptors, right? Both expressed in the prefrontal cortex, pyramidal neurons, and interneurons. So, of course, on this dorsolateral prefrontal cortex, you have those dopaminergic neurons. The D1 receptors are dominant. They modulate working memory by regulating signal-to-noise ratio in cortical microcircuits. That's good to know. In the dorsolateral prefrontal cortex, it's the D1 receptors that modulate working memory. Optimum D1 optimization enhances task-relevant firing. Too little or too much dopamine impairs performance, right? Too little dopamine is hypodopaminergic. Too much is hyperdopaminergic. So I think you have to get it just right in order to get things working very well here. Now remember, all of the substance abuse, like cocaine, amphetamines, and things like that, target the dopamine receptors. And they all result in the excess release of dopamine. And the intoxication is secondary to a hyperdopaminergic state, right? And so here, you can see here the D1 receptor here it modulates working memory by regulating the activities. Here, the source mesocortical projections from the VTM. This is from the meso to the cortex from the VPM. Okay. Yep. Next, glutamatergic system. The glutamate, remember, excitatory receptors. AMPA, remember that, and NMDA, remember, this is the receptor ecstasy activates. And metabolic glutamate receptors, these are the G proteins. All right. These functions are excitatory. They drive between pyramid neurons. And so these things turn things up. NMDA receptors are essential for working memory and persistent firing. NMDA receptors are essential for working memory and persistent firing. Here, pathophysiology. NMDA hypofunction implicated in schizophrenia and cognitive disorganization. So NMDA hypofunction, that is glutamatergic hypoactivity, is implicated in schizophrenia and cognitive disorganization. Make sense? Right. Next is the GABAergic system. Remember, glutamate turns everything on, GABA turns everything off. The glutamatergic receptors, or the NMDA receptors, are the targets of things like the ecstasy, like LSD, like PCP. It's going to like cocaine, like methamphetamines. It's going to hit this glutamatergic system and activate, cause the release of more glutamatergic system, and then makes everything all activated. Yep. Now the other drugs of abuse, like the benzodiazepines, like Xanax and Valium and all those things, the Xan, they target the GABAergic system and they turn everything off. And so here with GABA receptors, you have GABA A and GABA B on pyramid neurons and interneurons. And so for the interneurons, okay, the parvalbumin positive fast spiking cells critical for gamma oscillation and executive excitation, whatever that is, it sounds like it's very important. I'm sure you go back and read it yourself. Deficient reduced GABA function leads to poor cognitive inhibition and distractibility. Right. So look, GABA hypoactivity, meaning decreased suppression, means there's less filtering, means there's more noise. So there's less inhibition, and then there's more noise. And so concentration and focus is an active inhibition process whereby everything is inhibited or preventing from gaining access to expression, except that very one thing that you want to talk about. So that one stream of thought should come through. And that right there is what's proper GABAergic tone is. So that's proper GABA functioning. But if you have reduced GABA functioning, then it's less inhibition. So you get more noise, you get more being distracted, you get all of those things. You got it? Makes sense? And so this is one of the reasons why patients reach for benzodiazepines, because the benzodiazepines, I believe, they looked this up, target the GABA A site, right? And the benzodiazepines like Xanax, and basically you're activating this GABAergic system, shutting everything down, right? And then what happens with alcohol? I believe it's the B site. Alcohol targets the B site of GABA. What is alcohol? What? Liquid GABA? Alcohol activates GABA. GABA turns everything off. They have their shot of vodka and they get all relaxed. They feel at home, right? Things change, right? Hitting that GABA. GABA turned everything off, right? Next here, we also have the noradrenergic receptors. The receptors, the alpha 2A adrenergic receptors, are mainly postsynaptic in dorsolateral prefrontal cortex. Locus ceruleus function enhances working memory and attention by strengthening recurrent network connections. So it enhances working memory and attention by strengthening recurrent network connections. Drugs like alpha 2 antagonists improve dorsolateral prefrontal cortex function in ADHD and stress-related cognitive decline. Yeah, remember guanfacine, the alpha 2 agonist, leads to improvement. It's interesting, yeah. Also here, next, serotonergic system, basically the serotonin receptors, their function in mood regulation, cognitive flexibility, and impulse control. Relevance, dysregulated serotonin receptors are associated with impulsivity and mood disorders. And so an SSRI target here, SNRI, can target the noradrenergic and the serotonergic system. And so let's see, dysfunction and symptomatology, damage or dysregulation of the dorsolateral prefrontal cortex or its networks produce dysexecutive syndrome. Another word I use for dysexecutive syndrome is executive dysfunction, meaning there's very little purposeful or coordinated or sequential behavior. No goal planning behavior. It's just a person is simply reacting, responding to their ego, right? And so here, cognitive symptoms, look, impaired working memory, right? Poor planning and organization, right? Deficient set shifting, look, concrete thinking. Next, behavioral symptoms, apathy, poor judgment and impulsivity, distractibility and goal neglect. Look at these symptoms, yeah. Psychiatric manifestation, schizophrenia, dorsolateral prefrontal cortex dysfunction features, look, hypofrontality, working memory deficits, right? NMDA and D1 receptor dysregulation, right? This is a glutamate receptor, and this is a dopamine receptor, okay? For depression, reduce activation during cognitive salve, reduce serotonin and dopamine imbalance. That's why you may need an SSRI and also an antipsychotic, right? ADHD, impaired attention impulse control, low dopamine and norepinephrine tone. That's why a stimulant results in the release of dopamine and norepinephrine from the presynaptic neuron into the synaptic cleft, therefore helping with symptoms of attention deficit disorder right away, right? Obsessive compulsive disorder, look, overactivity and related surgery circuits, serotonin glutamate imbalance. Look, traumatic brain injury, executive dysfunction, that is diffuse frontal striatal disconnection. Okay, let's see here. here. They have here the neurotransmitter, the key receptors, and the functions, the symptoms. Okay, so dopamine, primarily D1-2 receptors, and this is the neurotransmitter that's primarily responsible for working memory, right? And this dopamine is just dysregulated in schizophrenia and ADHD. That makes sense, dopamine dysregulation. And then glutamate, okay? Same thing, glutamate receptor, NMDA is a type of glutamate receptor specifically that ecstasy binds to. And AMPA is another type of glutamate receptors. So this causes hyperstimulation, so persistent firing, right? And overexcitation results in the deaths of those cells. And once you get deaths of those cells, then you get the disruption of those networks. And I guess that's the process evolved into more cognitive fragmentation. Okay, GABA, the main inhibitory, which is GABA A and GABA B, is inhibitory and oscillatory control. And I'm not sure what the oscillatory control is. And basically, when you get dysfunction in the GABA receptor, you get disinhibition and inability to focus, right? Look at the noradrenergic, This is the alpha-2 adrenergic receptors. This is responsible for network stability and attention. Remember, in stimulants, you get the release of norepinephrine and serotonin, norepinephrine and dopamine from the presynaptic cell. And this is how we get that increased noradrenaline is going to give us more increased network stability and good attention. But the hypoactive levels or low levels typically results in stress and fatigue. Next, serotonin gives these, but it's responsible for mood and impulse control. Right? Depression, impulse control, also depression and rigidity. Would you like me to include a diagrammatic map of the P? Yes. Sure. Let me see what they give. It may take a minute. Let me look at these Brodmann areas. Executive functioning. This Brodmann area is really interesting. Brodmann areas 1, 2, and 3 make up the primary somatosensory cortex. Okay, this is almost there. Brodmann area divide the cerebral cortex into 52 regions based on the structure of the brain, based on the structure of the brain cells. Oh, wow. Each area is linked to a specific function, such as a movement, a vision, or a language. These regions are still widely used in branch research, neuroimaging, and clinical diagnosis today. Brodmann's map helped bridge the gap between anatomy and function, making it easier to study how the brain works. Despite being developed in 1909, Brodmann's system remains one of the most reliable and referenced tools in neuroscience. This is really interesting, because I think what I'm going to start doing is looking at my CT scans and stuff, and then look at the damage and see where the damage is to see if I can map it to a Brodmann's area. And if we look into the area and whatever area it is, and sort of understand the networking in that area, and if we understood the receptor profiles, then we have a good idea of the medications that we can use to target a certain network in that part to see if we can get some improvement on it. It's evidence-based way of sort of approaching this issue. Let's see here. The dorsolateral prefrontal cortex, is that right here? Okay. Dorsal mean, here's a prefrontal cortex. Dorsal is behind, lateral is to the side. Okay, here's the prefrontal cortex. Dorsal is behind and lateral is to the side. The dorsal behind, the lateral behind and lateral to the prefrontal cortex. Here's the prefrontal cortex here, dorsal behind and lateral. Wow. Network layout and connectivity. So, okay, the posterior parietal cortex, the dorsolateral prefrontal cortex, and what is that? Okay, superior temporal gyrus, the anterior cingulate gyrus, anterior cortex, the dorsal striatum here. Okay, the receptor profile, look, the dopamine receptor, D1 and D2 for schizophrenia, ADHD, the glutamate molecule NMDA, which is the glutamate receptor, primarily the ecstasy targets, and then here's the other two for cognitive fragmentation, GABA A and GABA A for benzodiazepine sites, GABA B for alcohol. When it's dysfunctioning, you get disinhibition, poor focus, right? Alcohol withdrawal, right? Noradrenaline, alpha-2 adrenergic receptors, stress, basically that network sensitivity. When it malfunctions, you get a lot of stress, you get a lot of fatigue. Yeah, okay, that sounds good. I think that's all I'm going to have for today on dorsolateral prefrontal cortex, guys. So I hope that's very helpful for you in your studies. If you have any questions, please feel free to like, subscribe, and share. Otherwise, it's been a pleasure. If you understand more about the dorsolateral prefrontal cortex, guys, this is the seat of the ego. Take care, guys. Read out. Ciao.